Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll walk you through the fundamentals of Amazon Redshift, AWS's fully managed petabyte-scale data warehouse service. We'll explore key concepts like how Redshift stores and processes data, node types, table design, loading data, and performance tuning. Let's get started. Amazon Redshift is a fully managed, cloud-based data warehouse service built to handle petabyte-scale analytics on both structured and semi-structured data. It's designed for speed, scalability, and ease of use, enabling organizations to run complex queries and generate insights from massive data sets in a matter of seconds. At the core of Redshift's performance is its massively parallel processing architecture, or MPP. This architecture breaks up large analytical queries and distributes them across multiple compute nodes, each working on a portion of the task in parallel. This not only accelerates processing times, but also allows Redshift to scale horizontally with ease as data volumes grow. Redshift stores data in a columnar format, which is optimized for analytical workloads. Combined with built-in compression, this significantly reduces the amount of data read from disk, improves cache efficiency, and speeds up query performance. One of Redshift's most powerful features is Redshift Spectrum, which lets you run queries directly on data stored in Amazon S3, even if that data spans exabytes. This allows for a seamless extension of your data warehouse into your data lake, enabling analytics across both local and external data sources without the need to move or duplicate data. From a security and governance perspective, Redshift offers fine-grained access controls, integration with AWS IAM, and support for industry compliance frameworks such as SOC 2, HIPAA, and GDPR, helping enterprises meet strict regulatory requirements. In terms of deployment, Redshift offers flexibility to suit a variety of workloads and team preferences. You can choose a provisioned cluster model if you want full control over compute and storage resources, or go with Redshift Serverless, which automatically provisions and scales resources based on demand, allowing you to focus on your data and queries rather than infrastructure. A node in Redshift is a compute unit within a Redshift cluster that performs the core operations of query processing, data storage, and parallel execution. Each node provides a set amount of vCPUs and RAM to process queries and perform calculations in parallel. In a Redshift multi-node cluster, each node processes a portion of the data, and query execution is massively parallel, resulting in faster performance for large datasets. Redshift offers different types of nodes tailored for specific use cases. Dense compute DC2 nodes are purpose-built for performance-intensive workloads that require low latency and high-throughput query execution. These nodes are equipped with high-speed solid-state drives, SSDs, which significantly reduce data access times and improve I/O operations. This makes DC2 nodes an excellent choice for use cases involving interactive dashboards, real-time reporting, or complex analytical queries over smaller to mid-sized datasets where performance is paramount. Because of their SSD-backed architecture, DC2 clusters can deliver fast query results even when under heavy concurrency or complex filtering. In contrast, dense storage, DS2 nodes are optimized for cost-effective, large-scale data storage. These nodes use traditional hard disk drives, HDDs, which offer higher raw storage capacity per node, but at the cost of slower I/O performance compared to SSDs. DS2 is well suited for workloads that deal with very large data sets, where queries are batch-oriented or less time-sensitive, and where storage cost efficiency is a higher priority than speed. Examples include long-term data archiving, historical trend analysis, and batch processing jobs. The most modern and flexible option is the RA3 node family. These nodes decouple compute from storage, allowing you to scale each independently. RA3 nodes use Redshift Managed Storage, RMS, which automatically offloads less frequently accessed data to Amazon S3, providing a cost-effective solution without compromising performance for active data. In a Redshift multi-node cluster, data processing and query execution follow a massively parallel processing model. This means that large data sets are broken into smaller segments, and each compute node handles a portion of the workload independently and simultaneously, greatly improving performance and reducing query times. At the heart of this architecture is the leader node. This node doesn't store any data itself. Instead, it's responsible for coordinating query planning, optimizing execution strategies, and distributing tasks across the compute nodes. Once the compute nodes finish their work, the leader node aggregates their results and returns the final output to the user. The compute nodes are where the heavy lifting happens. They store the actual data and perform the query execution in parallel. Each compute node is further divided into slices, allowing for even finer-grained parallelism during query processing. This architecture, featuring a central leader node and multiple parallel compute nodes, is what gives Redshift its power to handle large-scale analytical workloads efficiently. The type of storage used in the compute nodes plays a crucial role in performance and capacity. DC2 nodes are equipped with solid-state drives (SSDs) and a great choice when speed and responsiveness are critical, such as with dashboards or complex analytical queries over smaller to medium-sized datasets. On the other hand, DS2 nodes use traditional hard disk drives (HDDs) and best suited for large, less frequently accessed datasets, where query performance can be traded off slightly for more economical long-term storage. RA3 nodes represent a significant evolution in Amazon Redshift's architecture, designed for modern analytics workloads that demand both scalability and efficiency. Unlike traditional node types, where compute and storage are tightly coupled, RA3 decouples them, allowing users to scale each independently based on their specific needs, making it especially suitable for dynamic or unpredictable workloads. At the core of RA3's architecture is Redshift Managed Storage (RMS), which offloads all persistent data storage to Amazon S3. This decoupling means you no longer have to pre-provision large, expensive local disks just to meet your storage demands. Instead, S3 serves as the durable, virtually unlimited back-end storage layer. When queries are executed, Redshift intelligently pulls data on demand from S3 into the local SSD-based storage of the RA3 nodes. This local storage acts as a high-speed cache, and Redshift uses a least recently used LRU algorithm to manage it, automatically keeping frequently accessed hot data local while pushing less used cold data back to S3. This tiered storage model ensures high performance for active data and cost-effective retention for infrequent data. In addition, the independent scaling capability of RA3 nodes provides unmatched flexibility. If your workloads require more processing power, you can scale up compute resources without worrying about the storage footprint. Likewise, your data can grow significantly without impacting compute capacity, keeping your cost structure efficient. This modern design not only leads to faster queries on active data, but also helps reduce total cost of ownership, especially in environments with unpredictable usage patterns or growing datasets. Table design is a critical factor in achieving optimal performance and efficiency in Amazon Redshift. One of the core architectural advantages is that Redshift uses a columnar storage format, which significantly improves performance for analytic workloads. By reading only the necessary columns for a query, Redshift reduces I/O and enables more efficient data access. This columnar design also supports high levels of data compression, further improving query performance and lowering storage costs. To make the most of this architecture, it's important to choose efficient data types. For instance, using small int instead of integer where appropriate can help reduce memory usage and improve overall performance. While denormalization is a common practice in Redshift, especially for simplifying joins and speeding up queries, it's important to avoid creating excessively wide tables with hundreds of columns, as this can negatively impact performance and resource utilization. Another powerful optimization technique is the use of materialized views, which allow you to pre-compute and store the results of expensive queries. These are particularly useful for dashboards and recurring aggregations, reducing query times dramatically. It's also worth noting that unlike traditional relational databases, Redshift does not support indexes on tables. Instead, performance is driven by smart table design, effective use of sort keys, distribution styles, and optimized queries. Amazon Redshift supports the definition of primary keys, foreign keys, and unique constraints, but unlike traditional relational databases, these constraints are not enforced. Instead, they serve as metadata or advisory declarations that can help Redshift's query planner make better optimization decisions. For instance, specifying a primary key does not enforce uniqueness in the data, and defining a foreign key does not ensure referential integrity between tables. This means that Redshift won't validate the correctness of the data during insert or copy operations, and it becomes the responsibility of the data pipeline or upstream systems to ensure that the data adheres to those constraints. Even though these constraints aren't enforced, they can still be valuable for performance tuning, particularly in star schema designs, which will be discussed later. Declaring primary keys on dimension tables and foreign keys on fact tables can help the optimizer generate more efficient query plans by reducing unnecessary joins or leveraging more parallel execution paths. It's important to understand that no indexes are created behind these constraints, as Redshift relies on sort keys and distribution styles for query performance, not traditional indexing mechanisms. As such, key constraints are best used in environments where data comes from trusted and validated sources, such as controlled ETL processes or upstream OLTP systems. Ultimately, while key constraints in Redshift don't enforce data integrity, they are still an important part of effective table design when used thoughtfully and in the right context. The star schema is a foundational data modeling pattern that strikes an ideal balance between performance, simplicity, and scalability, especially in OLAP, online analytical processing environments like Amazon Redshift. Its design centers around a large fact table, which stores granular, measurable business events, such as sales transactions, order quantities, or revenue. This fact table is surrounded by multiple dimension tables, each describing the who, what, when, where of those facts, such as customer information, product details, promotional campaigns, or time periods. What makes the star schema particularly powerful in Redshift is its denormalized dimension tables. Instead of spreading related attributes across multiple tables, each dimension includes all necessary attributes in a single, flattened structure. This not only simplifies SQL joins, but also boosts query performance, as Redshift can efficiently scan and aggregate columnar data without navigating through layers of normalization. From a data engineering perspective, the star schema is intuitive to build and extend. You can add new dimensions, say a new marketing channel, or introduce additional metrics in the fact table without reworking existing queries or reports. Its clarity also benefits end users. Analysts and data scientists can easily understand the relationships and build their own queries and dashboards. The structure of a star schema is also ideal for materialized views, which can be used to pre-compute joins and aggregations. In Redshift, this can lead to dramatic performance improvements for high-traffic dashboards or periodic reports, especially when dealing with large volumes of data. Overall, the star schema aligns naturally with Redshift's MPP, massively parallel processing, architecture, and columnar storage model. It's a time-tested pattern that delivers fast performance, is easy to manage, and scales well as data complexity and volume grow, making it an essential strategy for any serious analytics workload on Redshift. This illustration presents a classic star schema, a widely used dimensional modeling approach in data warehousing, particularly suited for analytical workloads in platforms like Amazon Redshift. At the center of the schema is the sales order fact table. This table holds measurable, transactional data, such as sales records. Each row in the fact table typically represents a unique event or transaction, such as an order. The fact table contains foreign keys that link to each dimension table and includes numerical measures or metrics that are subject to aggregation, like quantity sold or revenue, though these are represented with placeholders here. Surrounding the fact table are four dimension tables which provide descriptive context to the facts. Customer dimension contains attributes related to customers, such as customer ID, name, address, and email. These fields help in slicing and dicing the sales data by customer demographics or geography. Product dimension includes product ID, product name, SKU, and product line. This dimension helps analyze sales by product categories or SKUs. Promotion dimension. This dimension adds marketing context by storing details like promotion ID, coupon code, promotion type, and start date. It enables analysis of how different promotions impact sales performance. Date time dimension, a standard dimension in analytical models. It breaks down the date ID into useful components like year, month, and quarter, allowing time-based analysis and trend identification. The relationships from the fact table to each dimension table are based on foreign key constraints, though Redshift doesn't enforce them. They're used primarily for query optimization and logical data integrity. Loading data into Amazon Redshift is a foundational step in setting up a high-performance analytics environment. The most efficient and scalable method is using the copy command, which supports parallel loading of large volumes of data from sources like Amazon S3, Amazon EMR, DynamoDB, and even remote hosts via SSH. This command enables Redshift to ingest data quickly by distributing the workload across all nodes in the cluster. Redshift is highly flexible in terms of data format support. It allows loading data in a variety of formats, including CSV, JSON, Parquet, Avro, and fixed-width files. Additionally, the copy command supports inline data transformations such as column mapping, date formatting, and applying default values, which minimizes post-load processing. Amazon S3 often serves as the primary staging area for data loads into Redshift. When data is stored in compressed columnar formats like Parquet, it can significantly reduce load times and I/O overhead, making the process more efficient and cost-effective. For more interactive or programmatic loading, JDBC or ODBC clients, the Redshift Data API, and AWS Glue can be used to insert data, especially for smaller datasets or for streaming ingestion. AWS Glue also allows users to catalog, clean, and transform data before loading it into Redshift, creating a seamless ETL workflow. Redshift includes built-in support for error handling during data loads. You can log errors, skip bad records, and retry partial loads to ensure that your ingestion process is both resilient and transparent. These features help identify and resolve data quality issues quickly. To maximize performance, it is recommended to follow best practices such as loading from multiple files in parallel, compressing files, example using gzip or LZO, aligning file structure with table schema, and using manifest files when working with large or partitioned datasets to ensure consistent and reliable loading. In Amazon Redshift, data distribution is a foundational concept that directly impacts query performance, scalability, and overall system efficiency. Redshift is built on a massively parallel processing (MPP) architecture, meaning it divides large datasets into smaller chunks and processes them simultaneously across multiple compute nodes. Within each node, data is further split into smaller units called slices, enabling highly concurrent execution of queries. How the data is physically distributed across these slices determines how efficiently queries can be run, especially for complex joins and aggregations. To control this, Redshift provides several distribution styles, each designed to optimize different workload patterns. Key type distribution. Rows are distributed based on the hash value of a specified column, often a join key. When two large tables share the same key distribution on a join column, the data is collocated on the same slices, which minimizes data shuffling between nodes and greatly improves join performance. Even type distribution. Data is spread evenly across all slices, regardless of content. This is the default distribution style, and it's useful when there's no obvious key for joins or when the table is a large fact table that doesn't need co-location with other tables. All type distribution. The full table is copied to every node in the cluster. While this introduces some storage overhead, it's very efficient for small, frequently joined dimension tables because it completely eliminates the need for data movement during joins. Redshift also offers an auto distribution style, which intelligently adapts to the table's characteristics. When a table is small, auto defaults to all distribution to optimize for performance. As the table grows, Redshift automatically switches to even to avoid excessive duplication and manage scalability. This dynamic behavior reduces the burden of manual tuning and helps maintain performance as data volumes change. Selecting the wrong distribution style can cause data skew, where some nodes are overloaded while others sit idle, or lead to cross-node data shuffling, which increases query latency. Therefore, understanding the nature of your data, and choosing an appropriate distribution strategy is essential for optimizing Redshift workloads and unlocking its full parallel processing power. In Amazon Redshift, sort styles are a powerful optimization mechanism that directly impacts how efficiently your queries run, especially when dealing with large datasets. Sort styles govern how data is physically ordered on disk, and they work hand in hand with zone maps, which track the minimum and maximum values of sorted blocks. When Redshift executes a query with filters, it can use these zone maps to prune out entire blocks of data that don't meet the filter criteria, significantly reducing the amount of disk I/O and speeding up query performance. You define sort styles at the time of table creation, and altering them later typically requires unloading and reloading the data. So making an informed choice early in your schema design process is key to maintaining efficient query execution as your data grows. Redshift offers three primary sort styles. Compound sort key. Default. This sort style organizes data by the first column in the sort key, then by the second, and so on, like a nested hierarchy. It's ideal for time series or range-based queries, such as filtering by date. However, if your queries don't leverage the leading columns, this style offers limited benefit. Interleaved sort key. Unlike compound keys, interleaved keys treat all columns with equal weight. Redshift maintains a balanced sort order across all specified columns, making this sort style more appropriate when your queries filter on different columns or combinations, not just the first one. However, interleaved keys come with additional maintenance overhead and are better suited for read-heavy workloads with diverse filtering patterns. Auto sort style. Introduced to support more dynamic environments, Auto lets Redshift decide how best to sort the data, or whether to sort at all, based on observed query patterns. It's particularly useful when query behavior is not yet predictable, or when you prefer Redshift to optimize sort strategy over time. Choosing the appropriate sort key and style can make a noticeable difference in query performance, maintenance cost, and overall system responsiveness. For large tables and frequently queried datasets, it's worth analyzing your access patterns and designing with sort styles in mind. Doing so enables Redshift to capitalize on its MPP architecture and deliver consistently fast performance. Amazon Redshift's columnar compression, or column encoding, is a key feature that enables both cost-effective storage and high-performance analytics. By storing data by column instead of row, Redshift is able to apply customized compression techniques to each column independently, taking into account the specific patterns and characteristics of the data stored in that column. For instance, a column with repeated values might benefit from run length encoding, whereas a numeric column with gradually increasing values may be better suited for delta encoding. Redshift supports a variety of encoding types such as LZO, zstandard, bytedict, and more, each optimized for different data shapes. To identify the most efficient encoding for each column, you can use the Analyze Compression command. This tool analyzes a representative sample of your table's data and recommends the best encoding types based on compression potential. It's a practical step to take before large data loads or when optimizing table design, especially for large fact tables. When applied effectively, Redshift's compression can lead to massive storage savings, often reducing data size by 70% or more. These savings not only lower storage costs, but also enhance query performance, since less data needs to be read from disk during execution. This is particularly important in analytics, where large volumes of data are scanned frequently. Compression is applied during the data loading process, such as through the copy command. Once the data is written, Redshift does not automatically re-encode it. So if you alter a table's structure or data distribution, you'll need to reload or reorganize the table to update the encoding. For even more efficient data handling, it's a good idea to load data using columnar file formats like Parquet or ORC, which support native compression. These formats not only reduce the volume of data transferred, but also improve the speed of ingestion into Redshift. Columnar compression in Redshift isn't just about saving space. It's an important part of your performance and cost optimization strategy, making it essential to consider when designing tables and planning data ingestion. Workload management, WLM in Amazon Redshift, is designed to control how queries are queued and how system resources such as CPU and memory are allocated across these queries. It allows for efficient management of query concurrency and ensures that resources are distributed in an optimal way to maintain performance. Redshift allows you to configure multiple WLM queues, enabling different workloads, such as ETL jobs, reporting queries, and ad hoc analyses, to each have dedicated resource slots. This segmentation ensures that heavy or complex queries don't starve simpler, quicker queries of resources. To handle spikes in demand, Redshift offers concurrency scaling, where it can automatically add transient clusters to handle a burst of concurrent queries, effectively reducing wait times and improving throughput during high-demand periods. WLM also provides powerful tools for query prioritization and timeouts. You can set up different priorities for different queues, determine memory allocation, and define time limits to ensure that critical workloads are executed promptly while preventing resource hogging. For more granular control, queries can be routed to specific queues based on user groups or query labels. This allows for targeted resource management, ensuring that different types of users or queries don't interfere with each other. Additionally, Redshift offers short query acceleration (SQA), which automatically detects short-running queries and bypasses the queue, enabling fast execution for lightweight queries without waiting for longer-running jobs. If you prefer simplicity, you can opt for automatic WLM mode, where Redshift will automatically manage queues and memory allocation, using machine learning to adjust settings based on historical workload patterns. Finally, Redshift provides robust monitoring tools like query insights, system views such as STL_WLM_query, and performance metrics available through CloudWatch, which help you monitor and fine-tune WLM configurations to optimize query performance continually. Amazon Redshift is designed with elastic scalability at its core, giving you the power to scale compute and storage independently, which is especially valuable when using RA3 node types. With RA3, compute resources can be adjusted based on workload demands, while storage is handled through Redshift Managed Storage (RMS), which resides in Amazon S3. This separation means you don't have to over-provision local disk just to get more compute power or vice versa, providing fine-tuned performance control and significant cost efficiency. To help organizations respond quickly to changing resource requirements, Redshift includes Elastic Resize, a feature that enables fast, automated scaling of compute nodes with minimal disruption. It's particularly useful for short-term scaling needs, for example, during peak business hours or end-of-month reporting, allowing your cluster to expand or contract quickly to match the demand, and then revert back when the load decreases. For use cases requiring more precise control over infrastructure, Redshift offers Classic Resize. This approach allows you to not only change the number of nodes, but also switch node types, such as upgrading from DS2 to RA3. While Classic Resize offers greater flexibility, it's a more time-intensive process. During resizing, the source cluster enters a read-only mode, ensuring that no writes or modifications occur until the process is complete. This helps maintain data integrity during the transition. To minimize any potential risks during resizing, Redshift supports snapshot-based backups. You can take a manual snapshot of your cluster and use it to launch a new cluster of the desired size or configuration. This is especially helpful if you want to experiment with different setups, create dev test environments, or simply ensure business continuity in case of an issue with the original cluster. In addition to manual and automated scaling options, Redshift's serverless offering allows for fully automated scaling with no infrastructure to manage at all. For organizations with unpredictable workloads, Redshift Serverless dynamically adjusts resources and pauses during idle periods to reduce cost, ideal for spiky or infrequent workloads. Amazon Redshift is architected with high availability and durability at its foundation, ensuring your analytics workloads remain resilient and your data stays protected, even in the face of unexpected hardware failures or system issues. A cornerstone of this durability is Redshift's automated backup system. By default, Redshift performs daily snapshots of your data and retains them for up to 35 days. These backups are securely stored in Amazon S3, providing durable and geographically independent storage. In the event of data corruption or a system failure, you can restore your cluster quickly from any point within the retention period, minimizing downtime and data loss. To further enhance resilience, Redshift supports cross-region snapshot replication. This feature is especially valuable for disaster recovery planning. It allows you to replicate snapshots to a different AWS region, ensuring that even if an entire region becomes unavailable, your data is safe and recoverable elsewhere. This helps businesses meet stringent RTO, recovery time objective, and RPO, recovery point objective requirements. On the hardware side, Redshift nodes use RAID-based disk configurations. In Redshift's distributed architecture, fault tolerance is achieved by replicating blocks of data across nodes and slices. So if a disk fails, Redshift can automatically reconstruct the lost data using replicas from other nodes, eliminating the need for manual intervention and reducing potential downtime. It's important to note, however, that single-node clusters do not benefit from this replication and must be restored from a snapshot if they fail. With RA3 nodes, Redshift further increases durability by offloading cold or less frequently accessed data to Redshift Managed Storage (RMS), which resides in Amazon S3. This not only reduces the need for large local disks, but also enhances data durability by storing critical data in a highly available and resilient object store. Redshift is also proactive in maintaining cluster health. It constantly monitors your environment and can automatically replace failed nodes, rebalance workloads, or initiate a recovery process to ensure continuity. This hands-off resiliency gives administrators peace of mind and keeps analytics workloads running with minimal disruption. Additionally, Redshift supports automated software patching and maintenance. These updates, covering performance improvements, security enhancements, and durability fixes, are applied seamlessly during your configured maintenance window, allowing Redshift to evolve with the latest innovations without compromising uptime. Amazon Redshift provides robust encryption capabilities to protect your data both at rest and in transit, ensuring its security across all stages of usage. By default, Redshift encrypts data at rest using AES 256 encryption, which applies to both data stored within the Redshift clusters and any backups stored in Amazon S3. This automatic encryption ensures that data remains protected when it's not actively being queried or used. In addition to data at rest, Amazon Redshift also ensures that data in transit is encrypted. All communication between your Redshift cluster and other AWS services, such as Amazon S3 or between client applications and the cluster, is automatically protected using SSL/TLS encryption. This ensures that sensitive information is secure as it moves across networks, preventing unauthorized access during transmission. Or API interactions with Redshift. All API requests, whether through the AWS SDK or CLI, are also encrypted using HTTPS. SSL/TLS. These requests must be signed using the SigV4 process. Redshift gives you additional flexibility by allowing you to use your own AWS Key Management Service, KMS, Customer Managed Keys, CMKs, for encryption. This option provides full control over your encryption policies and key management, offering a higher level of security tailored to your organization's needs. Alternatively, Redshift also supports Redshift Managed Keys, which automatically handle encryption for you, simplifying setup while still ensuring strong security measures. To provide even more control, Redshift supports column-level encryption, enabling you to encrypt specific columns of sensitive data within your tables. This allows you to secure the most critical information without having to encrypt the entire table, giving you more granular control over your security posture and helping you meet data privacy and regulatory compliance requirements. In terms of backup and disaster recovery, Redshift snapshots, whether automated or manual, are encrypted, ensuring that your backups are always protected. Moreover, if you need to copy snapshots across regions, the encryption is maintained, giving you confidence that your data remains secure even in different geographical locations. Amazon Redshift offers robust backup and restore capabilities to ensure that your data is always protected and can be recovered quickly if needed. By default, Redshift takes automated daily backups of your data at the cluster level, retaining these backups for up to 35 days. This provides continuous data protection without requiring manual intervention, allowing for reliable disaster recovery and peace of mind. Redshift also automatically manages the deletion of old snapshots based on your retention settings. While automated snapshots are retained for up to 35 days by default, manual snapshots can be kept beyond this period, providing you with long-term storage options when required. Redshift's backup mechanism is based on snapshot technology, where backups are captured at a specific point in time. Snapshots can be taken automatically or manually, giving you flexibility in how you protect your data. Additionally, cross-region snapshot copying enables you to copy your snapshots to different AWS regions, ensuring that your data is available even in the event of a regional outage. To optimize storage costs and backup efficiency, Redshift uses incremental backups. This means only the changes made since the last snapshot are backed up, rather than duplicating the entire dataset, which helps minimize storage usage and speeds up backup processes. For more control, Redshift allows you to take manual snapshots at any time. These are particularly useful for custom backup needs, such as before performing major updates or migrations. You can retain manual snapshots for as long as you need, giving you greater flexibility in how you manage data protection. Restoring data from a snapshot is a fast process. When you need to recover, you can restore an entire cluster or specific tables from a snapshot, which eliminates the need to reload data from source systems and significantly reduces downtime. Monitoring is a critical aspect of managing Amazon Redshift clusters, and the platform provides robust tools to ensure that your database performs optimally and remains healthy. Redshift also provides system tables and views, which offer detailed internal metrics and operational data. These system views allow you to monitor aspects like query execution, data distribution, and resource usage at a granular level. Furthermore, the ability to review query execution plans helps you understand how queries are processed, making it easier to identify inefficiencies, such as improper data distribution or missing indexes, and fine-tune your queries for optimal performance. For deeper performance analysis, Amazon Redshift Performance Insights offers a powerful solution. This tool enables you to drill down into the performance of your queries and clusters, helping you identify long-running queries, resource bottlenecks, and potential areas for optimization. One of the key tools for monitoring is Amazon CloudWatch, which integrates seamlessly with Redshift to provide real-time monitoring of critical metrics such as CPU utilization, disk space usage, read-write operations, and query performance. These insights allow you to keep track of your cluster's health and quickly identify potential issues. For security and compliance purposes, Redshift integrates with AWS CloudTrail, logging all API calls made to the cluster. This provides an essential audit trail for tracking changes, troubleshooting issues, and ensuring that your actions align with security policies. Additionally, audit logging captures all user activity within the database, logging queries and administrative actions. This is particularly useful for security audits, compliance reporting, and troubleshooting performance problems. Lastly, Redshift Advisor offers recommendations based on your cluster's usage patterns and workloads. It provides actionable insights to help optimize configurations, improve query performance, and better manage storage. Redshift Spectrum is a powerful extension of Amazon Redshift that allows you to query data directly from Amazon S3 without needing to load it into your Redshift tables. This makes it incredibly useful for running analytics on large volumes of semi-structured or infrequently accessed data that may not need to reside in your core data warehouse. At its core, Redshift Spectrum lets you define external tables that reference files in S3. These tables are read-only, and you can query them using standard SQL syntax alongside your regular Redshift tables. This allows for seamless integration of cold or archival data into your analytics workflows, all while maintaining a single query interface. To use Redshift Spectrum, you must have an active Redshift cluster, as it acts as the entry point for query execution. Once a query involves external data, it's handed off to a fleet of dedicated Redshift Spectrum nodes that operate independently from your main cluster. These nodes scan and process the data directly in S3 and return the results to your Redshift cluster, where any further processing or joining with internal tables takes place. One important architectural consideration is that your Redshift cluster and the S3 bucket must reside in the same AWS region. This ensures optimal performance and avoids cross-region data transfer costs or latency. In the accompanying illustration, you can see how this architecture plays out visually. The client connects to the Redshift cluster, which in turn orchestrates the query execution. When external data is involved, it delegates the heavy lifting to Redshift Spectrum's compute layer, which interacts directly with the underlying S3 storage layer. This architecture allows Redshift Spectrum to scale query processing power independently and cost-effectively. Aqua, or Advanced Query Accelerator, represents a major leap forward in how Amazon Redshift handles data-intensive workloads. It brings hardware acceleration and intelligent caching into the architecture, fundamentally changing how and where certain queries are processed. Traditionally, when a query is executed in Redshift, large volumes of data often need to be moved from storage into compute nodes for filtering, aggregation, or other transformations. This process can create performance bottlenecks, especially as data volumes scale. With Aqua, that changes. Rather than moving data into the compute layer, Aqua introduces a high-speed, distributed cache that lives closer to the storage layer. This cache isn't just fast memory, it's backed by purpose-built hardware accelerators designed to perform operations like filtering, scanning, and aggregation directly on the data as it's retrieved, minimizing the need for data movement and reducing query latency significantly. For workloads involving large datasets and complex operations, Aqua can deliver up to a 10x performance improvement, especially for queries that rely heavily on scanning large fact tables, applying filters, or computing aggregates. The system intelligently keeps frequently accessed or hot data in memory, using a smart caching algorithm to prioritize what stays close for rapid access. One of the key benefits of Aqua is that it's completely managed and scales automatically. There's no configuration or tuning required. As your workload grows, Aqua dynamically adds processing capacity behind the scenes. This makes it ideal for variable or unpredictable workloads, where performance needs fluctuate. Because Aqua integrates seamlessly with your Redshift cluster, users and applications don't need to make any changes to take advantage of the performance gains. It's a transparent boost to query performance built directly into the Redshift ecosystem. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.